Thanks everyone for coming today and spending your time to learn a little bit about using hardware acceleration to change the economics of streaming. And when we're talking about the economics of streaming, we're not talking about the bandwidth charges and what you're charging the customers. We're talking about the infrastructure needed to support streaming at scale. And my name is Brent Yates. I'm the CTO of HellaStorm. We're an Atlanta-based company that spent the last 7 years developing IP specifically around how to accelerate cloud-native server deployments and edge deployments, primarily around streaming. And I've spent the last 25 years building FPGA-based designs to do those types of operations. So today we're going to talk about a little bit about how software is deployed in the cloud and how using hardware acceleration can make that better, and why it's absolutely required to do that. Otherwise, you spend more and more money building infrastructure when there's a more efficient way to do it. And the primary goal of this, of course, is to increase your return on your infrastructure investment. So let me talk a little bit about the types of hardware acceleration, because we're going to be talking about hardware in this talk. And in the upper left of this, you can see CPUs and GPUs, which you're all familiar with. Those are pieces of hardware that have acceleration parts within them that are driven by software. They're very flexible to use, but they don't give you flexibility in deciding which types of hardware you can put in there. So if you have a need for something to accelerate and the CPU or the GPU doesn't do it, then you can't change them. And over on the far right is an ASIC. That's an application-specific integrated circuit. Think of it as something like a NIC card or RAID controller. It's designed to do one thing. It does it very efficiently. And then you have this strange beast in the middle, the FPGA. It's a piece of hardware that doesn't do anything. You put it in a system and it's a blank chip. However, using software-like tools, you can build a GPU or a CPU or a NIC or a RAID controller using an FPGA. And that's what we're going to talk about today, is that particular type of hardware. Because if you put that in your servers, you can get those accelerations exactly where you need them for your software. So an FPGA is a field programmable gate array. It's a big blank sea of gates. Over the years, they've gotten bigger and bigger. And you use basically high-level languages to design the hardware within it. And since we are talking about hardware, I wanted to give you an example of an FPGA-based card. So this is a real piece of hardware. It's a PCIe-based card that fits into a standard server like a Dell 1U or RU server. It has network ports on the back of it, has inter-process communication for clustering, has a PCIe port to fit within the server. And within this, under the heatsink, is a field programmable gate array that sits between the network and the CPU in order to offload common functions used in the cloud. And this is the type of card we're going to be talking about today. And FPGAs that power these cards are big business. This is not an esoteric piece of hardware that no one uses. Microsoft is deploying FPGAs in every single one of their servers at the cloud. In fact, some reports say that they have the largest FPGA deployments in the world. They've realized the importance of having hardware that you can reconfigure to make their Bing searches go faster, to make their network inter-process communication better. But it's flexible. They can keep changing them over and over. Amazon provides them as part of their cloud deployments, but only for you to use as a service. They're not, as far as I know, are not using them to accelerate their workloads. Intel spent $17 billion to buy the second largest manufacturer of FPGAs, specifically to go into the data center. And Xilinx, the world's largest FPGA manufacturer, estimates a almost $7 billion total addressable market for FPGAs in a few years. It's big business. Eventually, it's going to be on every server. And we want to talk about why it needs to go on every server. But we can't really talk about hardware unless we talk about the software that runs on hardware. The whole reason we have servers is to run software. And modern software development has changed. It used to be that you write big monolithic applications that do one task. And if you need to do it faster, you instantiate another instance of it. The problem with that is it doesn't fit within the way CPUs work nowadays. CPUs have lots of cores and lots of parallelization. So you need to break your big monolithic application up in little pieces. So that's the way software developers are doing it. They're building smaller, lightweight pieces of software with the primary goal of disconnecting the software from the hardware. So you, as a programmer, you no longer have to know what operating system I'm using, how much memory does it need, how much storage. You focus on the problem, and the cloud takes care of running it on an appropriate piece of hardware. Now, when we talk about the cloud, it's not a place, it's a way of doing business. It could be an Amazon, it could be on your premise, and it could be a hybrid of that. So it's not the where of it that matters, but the way that you're trying to build these applications. So given that that's the way software is going, what are the implications of that? primarily we have thousands and thousands of these small lightweight applications that need to run on servers. But it turns out that servers are not getting faster at a fast enough rate to keep up with the demand. Server demand on the curve at the bottom has been falling off for decades. And now we're only seeing about a 3.5% year-over-year increase in CPU power, which means that assuming you don't find more efficiencies in your software, the only way you get faster is to throw more servers at the problem. And we call this the capacity gap. So the curve on the bottom is your CPU increase. The red curve is the demand, which currently for streaming video is increasing at over 35% year over year. So the problem is the only way to fill that gap is with more servers and more data centers and more power. It's not a very green solution. So we need to find a different way of increasing that efficiency. And the way everyone's moving toward is accelerated hardware. And there are those pieces of accelerated hardware that we talked about before, GPUs, ASICs, and FPGAs. So we believe specialized hardware is the only way you're going to get that efficiency gain and get you back on Moore's law of doubling performance year over year. The only way you're going to keep it on there is a product like this that allows you to reconfigure itself and adapt to the changing conditions so that you don't have to switch out your servers every year. You change out the code that's running in the hardware to be new hardware. And that's what we're talking about is reconfigurable hardware. And the threshold for making this pay off is very, very small. According to an MIT study, just a 2x improvement in efficiency pays off for millions of dollars invested in building specialized hardware. However, FPGAs are already developed. The IP is already there if you work with a company like us that has spent almost a decade developing these blocks for you. So your investment doesn't even have to be as much as a 2x improvement. The problem with FPGAs is they're very hard to use. It's almost the same level of difficulty as building an ASIC. It takes years to develop it. It takes a specialized team. Unless you're Microsoft with hundreds of engineers that are trained in this, it's a losing proposition to try to do it yourself. The CTO of Dell was talking about AI when he quoted that if you do machine learning and AI right, people don't know it's there. It's ubiquitous. And we believe it needs to be the same way for accelerated hardware. If you do it right, if we built our systems the right way, the programmers don't know it's an FPGA card, just as they don't care that it's a NIC or a RAID controller. They're just using the services. So we believe that that's the way that you need to go about doing these types of systems. So we came up with the 3 laws of reconfigurable hardware. First one is cause no harm to the programmers. You've got to build a system that fits within the way they work. You can't change the market and tell people they have to learn a new skill. You need to work within the way they're used to working. And second, you need to provide a benefit. It can't be a sea of empty gates. You can't go to Intel or Xilinx and buy a card and stick it in a server and expect anyone to do anything with it. Those chips don't do anything by themselves. They're a blank potential. We want to fill that potential. And then finally, it needs to be reconfigurable hardware. You could build an ASIC to solve a problem, to make your servers run super fast on your Bing searches if you're Microsoft. But if the industry changes, you've just sunk a lot of cost into hardware that you can't use. So it needs to be reconfigurable. And a card like this is something that does that. So features that we have, kind of the things that we've offloaded. Obviously network performance is one of the big ones. Object store, which is a high performance clustered file system, is a big one. We can do HTTP pattern matching, interprocess communication, cloud type storage operations. These are all examples of things that can be pushed into the specialized hardware that frees the software from having to worry about these common functionalities. So what does this actually really look like? Well, typically in these small lightweight services that you're running, these are the types of things that you're going to be doing. You're going to be running application logic. You're going to be doing local storage. You're going to be doing a global storage, because remember, these applications can run on any machine in the cluster, so they can't look at what the local storage is. They have to see a global view of that. And there are many products and things that can do this, but if you integrate them all into your servers, you get a very small temporal gap between the data and your processing, which helps improve performance. And that's the whole goal of this, is to make a single server faster, to make it be able to do more work, not by increasing the power that it uses or the clock speed, but by increasing the efficiency of it. So we believe that we can actually move all of those into this card, and we've done it. We have implemented HTTP processing so that we can pattern match on hundreds of thousands of rules, like regular expressions, of every request coming into the system. We've clustered servers using the hardware connection between these cards in order to see a coherent view of storage across all these boxes. We've given the individual containers localized memory structures that we can directly write into to increase the efficiency, which allows us to do high-speed logging and high-speed diagnostics. And if you've been to some of the other sessions, one of the big selling points of the future is data acquisition, not on the raw data videoing through the system, but who the video is being played by, how long do they look at it, what are they doing with it. All of those things can be recorded, but they all take CPU cycles. We've decided to push all those CPU cycles into the hardware. It's reconfigurable. If a customer needs that, we can drop it into the FPGA. And this is sort of a conceptualized diagram of what that is. The little green circles on the bottom are your microservices. The big red box are all the various things running in the FPGA. And with the main goal of making your software more efficient. And this is kind of a view of how it makes it more efficient. The idea is that you want to parallelize processing. So you have the CPU sitting there running some kind of task. While it's running, we can connect the FPGA up to network into storage and be moving the data directly from storage out the network or from the network into storage, independent of what the CPU is doing. However, you probably want the CPU talking to the FPGA to tell it what to do because it's the master in the system. A lot of the times you're deploying things at the edge and everybody's moving to AI and machine learning, but to make those very expensive cards efficient, you have to feed them data and you have to be very efficient at that. So rather than the data going through the CPU, we can make a direct path to the GPU. So now you've got multiple parallel systems all running at the same time with a very small hardware investment that's flexible and can change for the future. So the final analysis for us on the advantages of this is that an FPGA in every single server will make those servers multiple times more efficient. They're adaptable, they can change to existing and future conditions. And one of the things that our customers are very worried about is how many IOPS can they do? How many HTTP requests can they come in? The protocols around streaming are changing. The chunk sizes are getting smaller. The protocols are pushing up the number of requests per second that the servers have to do, and some of those servers are rolling over. You're hitting bandwidths on some of the big CDNs of 10,000 requests per second per server. And if you think about serving tens of millions of people, that's a lot of servers. However, we have demonstrated to them 100,000 IOPS on the same workloads, but just by adding in an expansion card. And if you follow the 3 laws of reconfigurable hardware, you aren't changing the way your company works. The software people don't have to change. They just have a new API, and they get the advantage of the acceleration. So let me talk about a real-life use case for this, and that's the content cache. And we talk about the CDNs, and one of the big things they have to do is move data around their networks from place to place and keep it in a cache. And there are many software applications that do this. Varnish, Nginx, Apache Traffic Server, they're all written to do the same kind of problem. A request comes in, they have to figure out who the request is for. They have to figure out how they need to massage that URL to make it into a common form. They need to hash it to figure out if you have it locally, pull it from storage if you do and serve it out the network, or if not, ask it from the next server up the stream. And eventually it'll get to the origin server that has the data and it all transverses back. It's a very repeatable common form. And one of the limitations of that is how many of these requests per second can you do? So by moving all of the common pieces of those applications into reconfigurable hardware and making it one of the options that you can run when you have a card like this in the system, you've left the CPU with doing only the application logic, the thing that's unique for your CDN, what the special sauce that allows you to optimize it better than other people and to get your servers to be more efficient. So what we've seen in running this content cache is that we can run these applications in a container. They don't have to be bare metal applications anymore. It makes it easier for the CDNs to adapt their servers to other uses because they don't have to take down the whole server. They just drop another container into it. We can hit full line rate, which on our card is about 40 gig per second, on a single 1U server and do over 200,000 requests for containerized application or containerized data. The CPU utilization and the power are low. We're talking less than 250 watts on a 1U server. Because we've stored all the data in, and not in memory, but in persistent memory like NVMe storage, you can restart the server and not lose your cache. And this is a big deal for companies that have hundreds and thousands of these caching boxes. They're constantly doing waves of updates, of firmware updates, which means they're taking their servers down. And every time they come back up, they've got to pull all the content back from the upstream origin servers. We're fast enough with NVMe drives to do over 118 gigabits per second of random read data on a single box. And with no specialized software or software knowledge needed from the people writing applications, it can be a multi-tenant containerized server at the same time it's doing a content cache, because they don't have to know about the hardware, it just provides these services. Another one of our customers is a company called Streaming Global. They use HTTP processing to do live streaming. So they want to hit cloud-based storage for doing streaming. They've practiced on the cloud using Amazon, using Microsoft's network, using just standard cloud servers. But in their larger deployments, they wanted to look at building out their own infrastructure. So they came to us to see how they could do that. Using the same server with no reconfiguration on the hardware, we were able to wrap the storage into the same API used by Microsoft Azure. And they were able to point their software at us and get a huge increase in performance and efficiency. So a single 1U server could handle 20,000 of their live streaming customers. Cluster them together, you get you get better reliability with more than 40,000 simultaneous viewers. And it was minimal software changes on their part. And it built a system that is flexible. So now they can do the same thing. They have control of the edge. They can start getting more data analytics now from their customers. They can process all that without having to add more machines. So that's the reason why we want to see FPGAs in every server. Whether it's a card like ours or someone else who wants to build to a similar API, it gives you advantages on efficiency, on power, on being able to adapt to the future. So I think I went pretty quick there. But if there are any questions on the hardware infrastructure and how this is going, I'd be happy to answer them.
Hold on, I'll bring a microphone around. Very good presentation. You all know what FPGA stands for, just in case that's the trivia question. Question, anybody? No? Did he satisfy everything?
Well, thank you very much.
Do you have anything else you want to say? All right, well, big round of applause for Brent.